Life on Venus, survival in the atmosphere of hell. What if humanity tried to survive not on the surface of Venus, but in its sky? Venus is the second planet from the Sun. Its surface temperature reaches about 470 degrees Celsius, and the pressure is 92 Earth atmospheres. The air is composed of thick carbon dioxide, filled with sulfuric aerosols. There is no water and no breathable atmosphere. But around 50 kilometers above the surface lies a unique layer where temperature and pressure are similar to those on Earth. This could be the place where humans might survive, if they learn to live among the clouds. Before we continue our journey through the unknown, take a moment to like this video and subscribe to join our growing crew of space survivors. Comment below, where should humanity try to survive next? A frozen moon? Or something even stranger? Why this could happen? Such a step might be driven by a shortage of resources on Earth and the need to find an environment capable of supporting autonomous life. Venus is the closest planet with a dense atmosphere that provides enough buoyant lift to support massive floating structures. Unlike the Moon or Mars, Venus's gravity, about 0.9 times that of Earth, is close to our own, making long-term habitation easier without muscle or bone loss. Another advantage is its energetic accessibility. The solar flux near Venus is twice as strong as near Earth, meaning solar systems could easily provide continuous power even within the clouds. Together, these factors make Venus one of the few realistic options for large-scale survival beyond Earth. How it could be implemented? To survive in Venus's atmosphere, humanity could rely on a combination of already known technologies. Floating stations. Structures made from lightweight polymers and graphene composites, filled with oxygen-nitrogen mixtures lighter than the surrounding Venusian air. These modules could stay afloat at altitudes of 48 to 55 kilometers, where the pressure is about 1 bar and the temperature ranges from plus 20 to plus 50 degrees Celsius. Protective shells. External surfaces would be coated with nanoceramic and fluoropolymer membranes that neutralize droplets of sulfuric acid and prevent corrosion. Energy systems. Primary power would come from acid-resistant solar arrays, supported by radioisotope generators for extended periods of cloud cover. The temperature difference between warmer upper layers and cooler lower layers could also be harnessed through thermoelectric modules. Resources for life. The planet's carbon dioxide atmosphere could serve as raw material for producing oxygen, hydrogen, and methane through electrolysis and catalytic reactions. Sulfuric acid could be decomposed into water and sulfur. Thus, a closed loop of oxygen, water, and fuel production becomes possible. The environment of Venus. The atmosphere of Venus consists of approximately 96.5% carbon dioxide and 3.5% nitrogen, with traces of sulfur dioxide, argon, and water vapor. The most aggressive factor is the aerosols of sulfuric acid, forming dense cloud layers between 45 and 70 kilometers above the surface. These clouds move at speeds up to 360 kilometers per hour, creating a phenomenon known as superrotation. The atmosphere circles the planet in just 4 Earth days, while Venus itself takes 243 Earth days to complete one rotation. At an altitude of 50 kilometers, where a colony could exist, the pressure is roughly 1 bar, and the temperature ranges between plus 20 and plus 50 degrees Celsius, comparable to conditions in Earth's lower atmosphere. This is the so-called golden zone of the atmosphere, theoretically suitable for human presence. Below this altitude, the environment becomes lethally hot, and above it, the air grows too thin to support stable structures. Survival would also require consideration of the high air density, about 50 times greater than that of Earth's atmosphere, which makes movement of aircraft more difficult but provides significant buoyancy. This effect could be used to maintain large floating platforms with minimal energy expenditure. Sources of energy. Solar radiation near Venus reaches approximately 2,610 watts per square meter, about twice the intensity found in Earth's orbit. Even through its thick cloud layers, enough diffused light penetrates to make solar systems highly efficient. This energy could be harnessed using several complementary technologies. Floating photovoltaic farms positioned in the upper atmosphere. Their placement above the densest cloud layers ensures consistent sunlight exposure and stable power output. Acid-resistant perovskite solar panels, coated with fluoropolymer layers that prevent corrosion. The efficiency of such systems could reach between 25 and 30%. Thermoelectric generators utilizing the temperature difference between the warm upper atmosphere, around plus 50 degrees Celsius, and the lower, hotter layers, around plus 200 degrees Celsius. This gradient allows for continuous power generation without the need for fuel. Radioisotope thermoelectric generators, RTGs, as backup power sources for critical systems, similar to those used in interplanetary missions by the National Aeronautics and Space Administration. The generated heat could be used for water purification, climate control, and carbon dioxide electrolysis systems. Thus, a colony floating in Venus's atmosphere could remain energetically autonomous, drawing power solely from sunlight and internal thermal gradients. Resources for survival. The atmosphere of Venus contains all the fundamental elements needed to sustain a closed life support cycle. Carbon, from carbon dioxide, the main feedstock for producing oxygen and hydrocarbons. Through electrolysis, carbon dioxide can be split into oxygen and carbon monoxide, which can then serve as raw material for the synthesis of methane, carbon-1 hydrogen-4. Hydrogen can be extracted by decomposing sulfuric acid or imported as metal hydrides. Combined with carbon monoxide, it produces water and fuel for reactors. Sulfur is a valuable industrial element, useful for creating polymers, batteries, and heat-resistant insulators. Nitrogen, which makes up about 3 to 4% of the atmosphere, can be used to form breathable air mixtures and support plant growth in biological domes. Water obtained from the atmosphere can then be split through electrolysis into oxygen for breathing and hydrogen for energy, forming a closed survival loop, where system byproducts are continuously recycled into new resources. Living modules. The colony's habitats would exist as floating complexes made up of airtight spherical or cylindrical modules. Each module would feature a multi-layered protective structure designed for extreme environmental durability. Outer shell, a graphene membrane coated with an acid-resistant fluoropolymer, such as fluorinated ethylene propylene, FEP. This layer reflects ultraviolet radiation and prevents contact with acid droplets. Intermediate layer, a structural foam or aerogel providing thermal insulation and stabilizing internal pressure. Inner core, an aluminum-carbon framework containing systems for ventilation, pressure control, and air regeneration. Inside, all modules would be linked by sealed tunnels, allowing movement between living quarters, laboratories, and technical sectors without exposure to the external environment. For operations outside, drone manipulators and repair robots equipped with acid-resistant casings would handle all maintenance tasks. Humans would have no need to leave the pressurized environment. Every procedure would be carried out remotely, ensuring both safety and sustainability in the skies of Venus. Living conditions inside the colony. Life in the upper layers of Venus's atmosphere would resemble life inside a submarine or an orbital station, with one major difference. The colony would not be surrounded by vacuum, but by a dense, hot, and chemically aggressive atmosphere. Each habitat module would function as a closed ecosystem, maintaining its own cycles of air, water, and sustenance. Atmosphere and climate. The internal pressure would be maintained at 1 bar, with a temperature of around 22 to 25 degrees Celsius and humidity levels between 40 and 50%. The breathable air mixture, nitrogen and oxygen, would be regenerated through water electrolysis and photosynthetic bioreactors. Vegetation in sealed agricultural chambers would not only produce oxygen but also help stabilize the crew's psychological state. Nutrition and production. Food would come primarily from hydroponic crops, microalgae such as spirulina and chlorella, and protein bioreactors. All organic waste would be processed in closed-cycle bioreactors, ensuring no material loss. To increase self-sufficiency, carbon-based nanostructures could be used in three-dimensional printing to manufacture spare parts from atmospheric elements. Lighting and circadian rhythm. Because Venus rotates extremely slowly, one full rotation taking about 243 Earth days, artificial lighting systems would create 24-hour day-night cycles inside the colony. Adjustable spectrum LED panels would simulate sunrise and sunset, helping maintain the natural circadian rhythm essential for human health. Human biological adaptation. Even with near-Earth gravity, life in an enclosed atmosphere would lead to certain physiological changes over time. Respiratory adaptation. A slightly altered air composition with higher nitrogen content would affect breathing. Over time, humans would adapt to lower partial pressures of oxygen, aided by gradual acclimation systems similar to hypobaric training chambers. Musculoskeletal system. With Venusian gravity at 0.9 g, the risk of muscle atrophy is minimal compared to Mars or orbital habitats. Nevertheless, long stays in confined environments would require regular exercise and centrifugal training rings, which simulate gravitational load through rotation. Psychological factors. The greatest challenge would be isolation. Residents would live without an open sky or natural sounds, surrounded constantly by the thought of acidic clouds beyond the walls. To maintain mental stability, virtual recovery environments would be used. Immersive digital spaces replicating the sounds and visuals of Earth, forests, water, wind, birdsong. Such systems have already been tested during long-term spaceflight programs. Social structure of the colony. A colony in the clouds of Venus could only function as a tightly organized system, where survival depends on precise coordination among all participants. Governance. The most efficient model would be technocratic, with a high degree of automation. Core parameters, atmosphere, energy, and resource balance, would be continuously monitored and adjusted by autonomous algorithms, while humans would serve as operators and analysts overseeing system performance. Resource distribution. Water, oxygen, and energy would be allocated through consumption quotas. A real-time monitoring network would optimize usage and prevent waste. Every member of the colony would have a defined role: engineer, biologist, medic, navigator, analyst, drone operator, and others. And resource access would correspond to each individual's function and responsibility. Social dynamics. In such confined conditions, communication and psychological compatibility are crucial. Before deployment, crew members would undergo psychogenetic testing to evaluate stress tolerance and cooperative potential. Conflicts would not be treated as moral issues but as technical risks to system stability. Problems to be analyzed, mitigated, and solved to preserve the colony's balance within the atmosphere of Venus. Potential risks and threats. Chemical corrosion. Even with multi-layer protective coatings, there remains a constant risk of surface damage caused by acidic aerosols. Continuous surface monitoring is essential, supported by automated repair drones that regularly apply new protective layers to maintain structural integrity. Atmospheric turbulence. Wind speeds reaching 350 to 400 km per hour can produce severe pressure variations. To counter this, colonies would rely on dynamic stabilization systems, gyroscopic rotors that continuously adjust and balance the floating platforms. Energy interruptions. Extended darkness on the planet's night side can last up to 60 Earth days. Each colony must therefore maintain substantial energy reserves in the form of chemical batteries and thermogenerators to ensure uninterrupted operation. Biological isolation. In such a completely sealed ecosystem, even minor infections could become catastrophic. Residents would undergo constant medical monitoring, while deoxyribonucleic acid banks would preserve genetic material for future generations. Long-term evolution of the colony. With stable operation over several decades, a Venusian colony could evolve into a permanent habitat. Advancements in materials and robotics would enable the construction of floating cities, multi-kilometer complexes connected through atmospheric transport corridors. The development of nanotechnology and automated production modules would allow the colony to self-replicate, manufacturing new components directly from atmospheric resources. This would give rise to a closed technobiosphere, capable of existing indefinitely without resupply from Earth. Over time, generations born in the clouds of Venus would form a population that had never seen solid ground. Their world would be an aerial ocean, where life unfolds between sunlight and acid, suspended in the golden atmosphere above the inferno below. Technological evolution and the possibility of terraforming. If such colonies maintained stability for centuries, technological advancement would inevitably reshape humanity's approach to the planet itself. Venus could evolve from a refuge of survival into an object of gradual planetary transformation. Atmospheric regulation. The main obstacle to life on the surface is the enormous concentration of carbon dioxide. To mitigate this, aerostatic chemical reactor factories could be stationed within the upper atmosphere. These airborne facilities would bind atmospheric carbon into carbonates or carbon nanomaterials, progressively reducing the greenhouse effect. Simultaneously, the electrolysis of carbon dioxide would produce oxygen and carbon monoxide, which could then be synthesized into water, methane, and organic compounds. Even partial atmospheric modification of this kind could alter the planet's thermal balance over time. Planetary cooling. One long-term strategy could involve the deployment of orbital solar mirrors around Venus, reflecting a fraction of incoming sunlight to reduce the total energy absorbed by the atmosphere. Calculations suggest that reflecting only 5 to 10% of solar radiation could lower surface temperatures by several hundred degrees over the course of a few centuries. This gradual cooling could render the lower atmospheric layers suitable for industrial operations or semi-habitable environments. Utilization of local resources. Beneath Venus's dense clouds lie rich deposits of metals, iron, nickel, and aluminum. Drone miners, designed for short-duration descents, could collect surface samples and deliver them to higher modules. The planet's extreme pressure and heat could be harnessed for energy-intensive reactions or for manufacturing ceramic and refractory materials. Step by step, the colony could transform into a fully developed industrial civilization, living not against its environment, but in harmony with it. A species that has learned to survive and thrive within the very heart of a planetary inferno. What if humanity's survival depended not on escaping to new worlds, but on learning to adapt to the ones that already exist? Venus stands as a symbol that even in the most hostile environment, it is possible to find a balance between danger and life. Here, the sun is closer, yet its light never touches the surface. Here, the atmosphere kills, and yet it also saves, holding human cities aloft on its swirling winds, like drops of air that never fall into the fire below. A humanity that learns to live within the clouds of Venus will understand that life does not require solid ground. It only needs stability, oxygen, energy, and the will to adapt. Perhaps thousands of years from now, these floating cities will feel ordinary, and the people born in the Venusian skies will see them as their natural home, a world where Earth is only a legend, and the clouds are part of daily life. And if one day another civilization discovers the remnants of those drifting human platforms, suspended within the acidic clouds of Venus, it will see a message written in the silence of the sky. Life does not seek comfort, it survives wherever there is even a chance.